All right, so welcome back. This is part two of chapter four. So again, one of the most common used method of connecting devices into networks, either home or businesses, and it's gaining momentum as we speak. It's wireless. So wireless is everywhere, and when you're using wireless, all right, when we use wireless using a device such as this, known as a wireless access point. So a wireless access point does and can allow computers. It works as a bridge that allows two wireless devices to communicate with each other. This is given that both all devices are configured properly. For instance, the wireless access point is listening at a given channel, and also an SSID and password keys, and the wireless devices are basically doing exactly the same thing. And we can do a little demo once we're so wireless access points really do act as we're called as a router if you want. All right, let's move on to data link protocols. Let's talk about the data link protocols. All right, the data link protocol, if you remember, again, this is the OSI model starting by the layer in the top 7, going all the way down to a data link layer. And if you remember, it is at the data link layer that that packet are given MAC addresses. The MAC addresses information of both the sender and receiver is being added, as we're going to see here. So watch this. It is at layer 2. By the way, data link layer is also known as layer 2. Layer 2 of the OSI model. And you can see at layer 2 what is added: the destination NIC MAC address and the source NIC MAC addresses are being added here. So the MAC addresses, the destination and the source MAC addresses, it is crucial to understand and know that in local area network, um, computers or end devices use MAC addresses to find each other and to communicate with each other. It's crucial to understand that a switch in any given network uses the MAC address table to forward packets from point A to point B. So it is at this layer 2 that the MAC addresses are added. And by the way, what as I hope there is a slide of it shows MAC addresses. I'm going to go back. There's no slide there. So MAC addresses are very similar to what it called. I'm going to show you this one in a demo. Very similar to IP addresses. The only difference is IP addresses are decimal values and are 32 bits, while MAC addresses are hex. They're not hexadecimals, and are 48-bit instead. The other difference, if you want, IP addresses do change every now and then. MAC addresses are constant. As a matter of fact, are burned into a NIC card and they don't really change. All right, I want you to pay attention to what's going to happen over here. So watch this. This is a given network, and I want to show you the media access control job at a different layer. So to explain what we have a computer in Paris need to communicate to another computer in, what we call it, in Japan. And between them, there's so many type of devices. There's switcher, there are routers, there are satellite dishes, there are also satellite and so on. What you need to understand, it's really the data link layer. At each hop, at each stop, the data link layer takes the frame and convert it, right, forward the packet into a new frame, into a format that the other device will understand. So here, the computer will take it would take the data, convert it into a frame that the router, because he's physically connected, so he's going to convert it into electrical pulses. The router then looks and say, hey, I am not physically connected to this device. The device I need to send to is a satellite. So I may be using some kind of microwaves if you want, or wireless communication if you want. So the router will send it to the dish, use it to the wireless dish, using some kind of microwaves or wireless. The dish then in itself need to send it up to the satellite, and satellite I uses some kind of media, some kind of different media So at each level, each device takes the frame and convert it into a format that destination device really understand. This is really important to understand. And you can see it is a data link layer protocol governs how to format a frame to use on different media. So different media requires different formats. So what makes that possible? It's a media access control. Providing access to media, again, this is a little bit what we talked about before here. You can see here we have two routers that are communicating with each other using a serial communication, right? Serial communications. And at each hop along the path from here all the way down for here if you want, each device router will accept a frame for a medium de-encapsulated. I'm not sure if you remember what is the encapsulation. The encapsulation and de-encapsulation process, it's a process where the user data or a PDUs it go through transformations, and then before it become frame and what we call forwarded. So that is known as encapsulation process. So data is being in the PDU is being encapsulated here, and once it reaches the destination, it'll be de-encapsulated, right? De-encapsulated, all right? And then forwarded to the new frame based on whatever medium is needed. Again, it is the data link layer that makes this possible. All right, we're moving to another concept, and this is known as, again, happens at the data link layer, and it's a media access control. All right, so the media access control, right? Using the media access controls sends sends frame on the network by looking at, or defines how to send frames in network by looking at its topology. If you ask what is topology, topology has two definitions. There are two types of topology, if you want, in any given network. There is something known as a physical topology, and there's a logical topologies. For instance, physical topology is straightforward, the way you look at it. And so for a computer, let's say for a file server, let's start from here. For a computer in a room 3 to access a file server in a data center, he needs to understand, he needs to figure out what kind of physical cable, how to physically get to it, and what kind of cable is there. This is known as physical topology. So this computer will have an understanding and how he's physically connected on the device and how he's going to reach the other device. That's this computer doing that. So this is known as physically. So in simple English, a physical topology is how computer or network devices are physically connected to each other. So you see cables, that's what you see. However, there's another topology that's very important in communication between devices, and this is known as logical topologies. So logical topology, as you see over here, is the way a network transfer frame from one node to the next. This logical signals path are defined by a data link layer. So it is the data link layer that defines how to logically use the physical topology and forward frame from point A to, for instance, to point B. For instance, you need to find out where is this computer, where is the computer that the data needs to go to. Is it here? This switch, for instance, may use MAC address to find out what is the server here. The router also use its MAC address to find out. The computer use also its MAC address to find out if the server he needs to talk to is in the same network. Is this machine here or on a remote? How does the computer do that? By the way, this is known as the ending process. This is known as the ending. And in the ending process, the computer uses his IP addresses and end it with its MAC addresses. Then the remote, the remote computer MAC addresses and its what do you call it? And its subnet mask. Then he compares the result of the ending. He does ending happens here using this computer MAC and subnet mask and remote computer MAC and subnet mask. Then the computer compares both the result of ending. If it is the same, this computer PC1, if you want, will clearly learn now that the computer he needs to talk to is right here. Otherwise, if it's different, he knows it's not on the same network, and he needs to forward this to the router, and the router job is to find out where this computer is located. So before I move on, just remember we have two types of topologies. There's the physical topology, physically using wire-to-wire, and there is a logical, which is how a switch or device find out how to forward frame from point A to a point B. The next thing, this is also physical if you want, and logical if you want. When this is a common physical, we do have common topologies for LAN and also common topologies for what they call it for WAN. The most common topology for WAN stands for wide area network, and I want you to understand this devices here are routers. That's where they are. So as there is a point-to-point, this physical topology is point-to-point. There is hub-spoke topology. It is a central, all the traffic goes to here before it goes anywhere. And then we have a mesh, which is a mesh if you want. Every device have multitude ways of communicating with every single device. All right, and we do this one usually for redundancy and also speed. All right. In a LAN, so remember I talked about topologies in a wide area network. What about local area network? Well, in a local area network, the topology we have a star, we have extended star, which is just an example of star. We have a bus, and we also have a ring. The most common used one, however, in a modern network is a star or extended. And this is basically define how this, what do you call it, how are they physically connected? See, they're connected as a star over here, they're connected like a bus over here, they're connected like a ring over here, and this is like a bus topology over here. This is a bus. However, there are different flavors of them. So this is, if we're looking at physical. If we're looking at logical, you may have a star like this, but physically that a star, by the way, is the most common topology, right? It physically looks like a star, but logically, these devices communicate like in a bus topologies. All right, when computers have a frame to exchange, they have multitude of ways of sending it. They can send what we know as there is a half duplex. So both devices can transmit and receive on the media, but only one can do it at the same time, right? This is only one can do it at the same time. In half duplex, like the old CB communication, when two are talking with CB, can you hear me? Yeah. Can you hear me? Yeah. That is known as a half. Yeah, there's two-way communication, but only one can talk at the same time. Another example of wireless LAN. Wireless LAN is an example of half duplex. Full duplex, when both devices can send and receive at the same time. All right, media access control. I want you to understand this concept very new. It's going to be new to you, and it takes some time to really understand. There is a term that we use especially in shared network, and we call it contention. And I'll explain what they mean. You guys need to understand that although we have three devices that need to talk to each other, I want you to understand that there's always one single cable. And the example I give my student, think about this house that have 5 teenagers and a single phone. Right? There's always fight over that phone, who's going to use it first. Guess what? In any given modern network, that is exactly the case. There is always one single wire. No matter how many devices you have in any given network, there's only really one single wire. Obviously, what's going to happen, every computer will fight over the wire, and this is known as contention. Contention. All right, well, here's another way of solving or trying to solve access to control access data without contention, without a fight, if you want. If we use something known as token ring. In the token ring, every single device has limited time, all right, and it will have its turn. Like, think of it as a microphone, think of it as a token. When this computer have a token, he will put his packet in what he called in a wire. And when this guy's done his job, the token moves to here, and this guy will do his thing. So the time is shared between all. There is no fighting. Everyone has time. All right. When there is a fight, when there's a contention, how do we solve this problem? How, when you have 10, 20 computers connected to a single cable using a contention, how they fight, how we organize this fight. By the way, although there's a fight, it is well organized. Computer use something known as carrier sense multiple access collision detection. In simple English, what does it mean? Every computer, PC2, before he puts his frames on the wire, he listens and makes sure that nobody is using it. When he knows that nobody is using the wire, then he puts his frame there. And he keeps listening to the entire path. If he detected collision, for instance, because PC1 went ahead and put his frame at exactly the same time, both of PC1 and PC2, I'm sorry for, and both of would apologize if you want, and PC1 would say, you know what, just because to avoid this from happening, I'm gonna wait one fraction of a second. And PC2 will say, oh, I will do exactly that. To avoid colliding with you again, I will wait one fraction of a second and half just to avoid you. This is known as carrier sense multiple access collision. We're not avoiding collision. Collision will happen, but when it happens, they will try to solve the collision problem. There's another one that is used in wireless, and instead of CD is AD, and it's CA, I'm thinking. CA, which is collision, what they call collision avoidance. Here we're not avoiding it, we live with it. But in wireless, we do try at all costs to really avoid it. And it, as you can see, is right here. So wide network uses CSMA /CD, while wireless uses CA. And another day I will explain to you the reason why wireless uses CA and wired uses CD. All right. So quickly, what did we talk? We have 3 minutes. In this chapter, we went over the physical layer protocols and services that support communication. We talk about a different type of media. We talk about the advantages and disadvantages, and we talk about the connectors. And I talked about, is it a good idea to make cable, not to make cables? And we talk about topologies and kind of compared talk about physical topology and also logical topologies. And in the physical topology, if you remember, I talked about the wide area network topologies, mesh, and so forth. And hub, spoke, and point to point. And I talked about local area network topologies. And I said in here, we'll talk about a bus, we'll talk about start, extended start, and also token ring if you want. And I said the most common use today is a start or extended start. Next, I talk about the data link layer and its job. How does it add at the last stage? It added the MAC address of the sender and the MAC address of the receiver, because MAC, all right, Ethernet uses MAC addresses for communication. Switches use MAC addresses to make decisions, right? And finally, I talked about no matter how many computers you have, I said you always need to remember there's only one medium, there's only one cable that every computer, all computers and network are sharing. Obviously, there will always be some kind of fight. And if there's a fight, they need to resolve. If there's collision, then they need to resolve those collisions. And I said in a wide network, devices use CSMA /collision detection CD, and a wireless network, we use CSMA /CA, which is collision avoidance. Another way, devices will avoid collision at all costs. We're done with part 2. I'm going to stop this and go to a lab, do a demo right now.